this. Okay, important announcement. Sydney messaged me yesterday and she said, both Allison and I forgot to mention that there's a talk or someone is presenting something on drinking water intake design, which is today at 11 in C140. She did say that half of you have a chemistry lab at that point, so you won't be able to go, but the other half, I don't know.
Allison was saying apparently it's pretty important. Someone you would want to talk to.
Yeah, I feel like, yeah, they should probably have it so that you can go. Probably slight oversight there. I don't know. I'm just the messenger. So there, I did it. I put a big note at the start of our notes. Who's the lab instructor? Is it Sydney? Oh. Were you guys just waiting out there? Waiting for a. Oh, wait.
I just arrived at the same time.
I was just talking about this drinking water intake design talk or presentation, or I don't know what it is. Like I said, I'm just the messenger. It's today at 11. It's C140. You might have a lab at that point. Okay. I think we're ready. Oh, and another thing. I'll mention it on Thursday. Hopefully I'll remember. I said we'll have a Zoom class on Tuesday after the long weekend. Can it just be a video? Can I post a video? And then you can watch it whenever you want. Then you can sleep in, and that's great. Okay. So I'm gonna change it. Video only for Tuesday. It is kind of the season where everything's piling up, so it's like, okay, I'll just lay low for a little bit. Tuesday, November 12th, I guess. But I'll post it before then. Depends on how far we get on Thursday, and so we'll see. But that's more for me, what video to post. Okay. We talked about exponential functions last day. We had some key features. Now I have to kind of remind myself here. We can have an exponential growth function like this, where it's growing, or we can have an exponential decay function like the green one here. And so what we said was, okay, our general function can look something like this. F of x is a times b to the power of x. And we notice that now x is in the exponent. Usually I say the power, but it is called an exponential function because it is in the exponent. Okay. Now, a is the vertical intercept of the graph. So when x is 0, the function is a. Why? Because if we look here, a times b to the power of 0, anything to the power of 0 makes 1. So a times 1. And so here, f of 0 is a times b to the power of 0, which is a times 1, which is a. Now, b is what determines the rate that the graph grows. And so when a is positive, we're going to talk about when a is positive, the function is going to increase if b is greater than 1, and the function is going to decrease if it's between 0 and 1. We also had let's see if it's on here. No. We also said that b must be greater than 0. Right? But between 0 and 1, right, it's some small number, then we have a decrease, and then if it's greater than 1, then we have an increase. So in this case, I'll add that the g of x has b somewhere between 0 and 1, and f of x has b greater than 1, is what that looks like. In both these cases, going back up here, a looks like it's 1, right? When x is 0, y is 1, and so a must be 1. So here, I'll do a must be 1 for both. Oh, nice. We talked about horizontal asymptotes. We've seen asymptotes before, right, where the functions approach a line, in this case at y equals 0, but it never touches on it, right? And so it's out of the domain, or in this case, it's outside the range. And so in our case here, we're going to have a horizontal asymptote at y equals 0. Now, if a is greater than 0, then it's going to be concave up, right? So a kind of a cup facing upwards. In both these cases, right, concave up, just kind of mirror around each other. And it's going to be concave down if a is less than 0. So let me see here. Concave up. Both of these are concave up, and concave down. Let's see here. If a is less than 0. Right. So kind of down, down versus up and up. The domain of the function is all real numbers. So we have this restriction on the range, but the domain, which is all the values of x, is we can put in any value of x and get a result. But then we said the range of the function, right? We said that b has to be greater than 0, not including 0, because we have an asymptote at y equals 0. And so the range of the function is between 0 and infinity. When you're sketching a graph of the exponential function, right, these two, this one here, the fact that it passes through a when x is 0 is useful. But also, if you let x be 1 instead, f of 1 is a times b to the power of 1, which is just going to be ab. And so here, the graph will pass through the points 0, a, and 1, a, b. And so if we have these graphs, and if you've got it printed out, the colors won't really go, but it does have the labels as well up top here, A, B, C, D, E, F. This very faint green D there. So what we're gonna do is we're just gonna try to match these functions to the graph. Now let's see here, let's start with 2 to the power of x. let's see here. F of 0, that's a good place to start, right? If I let x be 0, then I should get to a. Now, 2 to the power of 0 is 1. So if I go down here, it's one of these in this cluster. So that doesn't really narrow it down. That's all right. We'll keep going. Okay. And so it's one of these, not C, right? So that doesn't tell us very much. So then if we keep moving and we find f of 1 is 2 to the power of 1, which is 2. So when x is 1, y should be 2. So when x is 1, y should be 2. There, that's the ticket. That tells me that it should be f. So now f has been claimed.
So is it generally a good idea just to use like one?
Yeah, so, or x equals 1. So the trick is to put in x equals 0, find out what a is, and then put in x equals 1 and find out what ab is.
Okay.
Because you already found what a is, so then you'd be able to find what b is as well. Let's do the next one. I'll try to do different colors here. Although I sense I'm gonna run out. Oops. 3 times 2 to the power of x. Now notice the x is only on the 2, right? Not this projector, I tell you. Let's start by finding f of 0. So x is 0. 3 times 2 to the power of 0. 2 to the power of 0 is 1. So we get 3. Hey, score. Why? Because there's only one function when x is 0, y is 3, and so I already know that it must be c. Or maybe I'll put them down below here too. That's a bummer, because that was a quick win. How about 3 to the power of x? Oops. Let's find f of 0. 3 to the power of 0 is 1. Okay. That's not very helpful. Again, it's one of these clusters, except for f. We've already used f. But we still have A, B, D, E to choose from. And so we need to move on and find f of 1, which is 3 to the power of 1, which is 3. So when x is 1, y must be 3. 1, 3. And if we're really careful here, it's not the red one, it's the green one, which makes it D. How about e to the x? Do we know what it is already? We do. Why? Because these last two have b's less than 0, or less than 1, sorry, between 0 and 1, which tells me that, okay, those two have to be either a or b, right? They have to be decay, which leaves me with only 1 for e to the x. You can still go through the procedure, right? But it has to be e, because I've already used c, I've already used d, I've already used f, and so it has to be e because it's the only one that is left with growth. Right? And so here, I'm gonna go for e. since the next two are decay. So now, let's try green. If I have 1/2 to the power of x, if I find f of 0 is 1/2 to the power of 0, which is 1, no surprise, because the remaining two do go through 0, 1. And so we can confirm, but it doesn't tell us anything. But what if we do x equals 1? F of 1 is 1/2 to the power of 1, which is 1/2. So when x is 1, I'm at 1/2. Now, I can't really tell which of these. I think so. I suspect you're right. But let's do exactly what you just said. For 1/3 to the x, let's do f of 1 to compare the two. 1/3 to the power of 1 is 1/3. And so it must be b, and this one must be a. Because it has to be less than 1/2. Nice. Whew. Yeah. So just remembering that property, right? You can check at 0a and 1ab, plug in values. I mean, in theory, you could have plugged in x equals 2 to find out which one equals 4, but that's a lot of backtracking. Right? Okay. Any questions about that one? No. We're not going to do a lot of kind of graph transformations, but we can rewrite any transformed exponential as a times b to the power of x plus c, and then plus c, right? Remember that brings it up or down. And so that's going to move your horizontal asymptote. And so from the shift, right, the vertical intercept is now going to be moved from 0a to 0a plus c. Whether c is positive or negative, right, it still translates, because if you have a negative c, then it becomes a minus c. For example, if we have this graph here, in general, we said, okay, f of x is a times b to the power of x plus c. And we know that, okay, at x equals 0, because I can see that this has been shifted down. In fact, I can see that it's been shifted down 4 units, right? So -4. But let's just confirm. What are we going to do? I'm going to use x equals 0, and I know that it becomes -1 because I can see that it passes through -1. And so we see from the graph, f of 0 is -1, which means that f of 0 is a times b to the power of 0 plus c. And so f of 0 is a times 1 plus c, so a plus c. What about when x is 1? That's another one that we know, all right? And so x is 1. I'm going to say f of x is 2. f of 1 is a times b to the power of 1 plus c, which is 2. Okay. So, let's see here. Let's see here. Use dark blue.
Could we just automatically realize that -4?
Yeah, I'm considering it. A plus C. But then I'm probably also going to rely on this. So I can't seem to shake out the C just off the top of my head here. A horizontal asymptote at y equals -4. And so C must be -4. There. That's going to get us there. So if C is -4, then we can backtrack into f of 0 is a plus C, but it's also equal to -1. And so a plus -4 is -1. So a must be 3. -1 plus 4 is 3. Right. Then I can keep going from this one here. F of 1 is a times b to the power of 1 plus c is equal to 2. And so I have a is 3. I don't have b, but I have c is -4, and I know it's equal to 2. And so that's how I'm going to get ab plus c is equal to 2, but a is 3b plus -4 or -4 if you prefer. Right. Subtraction is just a special case of addition. And so now I have 3b minus 4 is equal to 2. And so solving for b, I get 3b is 2 plus 4, which is 6. So b must be 6 divided by 3. And I'm going to go for 2. Which means that the general function, if we map it back here, I have values for each of these now. So I can say, therefore, f of x is ab to the x plus c, which is going to be 3, oops, that was gross, 3 times 2 to the power of x minus 4, or plus -4 if you prefer. So now we know how to find the function or write the equation for a graph if we're given those key points, right? We needed 3 points. We use this one here. We use this one, or maybe I should use the same color. This one here, we use this one here, and in orange, we found the horizontal asymptote just by looking at it. Any questions about that one? It's all we're doing for graphs. That's nice. That's the only transformation that we'll be doing. Of course, you can do things like flipping it and stretching it and all that crazy stuff, but we'll leave that for a different course or never. How about that?
Never sounds good.
Never sounds great. Let's see here. That was section 2. I'm going to duplicate this. I don't like how it keeps it secret. What I'm doing keeps it a secret for you. Okay. This section is on exponents and logs. And so exponential functions, we just had a look at exponential functions. And so now we're going to talk about logarithmic functions. And so the thing about logs is now they're relatively easy to work with and compute using calculators. A lot of calculators just kind of calculate the logs. It used to be a very difficult thing. And so when I told my grandpa I was studying math, he kind of nodded and he said, like logarithms and stuff. I see. And so I was like, yeah, I mean, yeah, I guess we can do logs, but I also happen to really like logs. Now, a logarithmic function looks similar to the exponential function. It's just going to look something like this. And so a log is going to look something like this arch here. And spoiler alert, it's going to be the mirror image of the exponential function. And so around the y equals x line, but that's kind of too far ahead, jumping ahead a lot. We're going to have a horizontal asymptote at x equals 0. And so here we see that there's this horizontal asymptote at x equals 0. And in fact, if there's a horizontal asymptote here, right, it means it goes down, 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 and it keeps going until negative infinity, and it never touches x equals 0. And so what we're going to find is that for logarithms, we can't take the log of 0. You can try it on your calculator. It'll tell you math error or something like that. Illegal math. No, I wish it said illegal math. Oh no, I'm in the wrong menu here. Wait. If you take the log, oops, of 0, yeah, mine says math error, but I always read it as illegal math. And so here, what this means for us is we can't take a log of 0, but also we see that I can't take the log of a negative number. It only works for positive x's. Yeah. In fact, x must be greater than 0, not including 0, is the domain of the logarithmic function. That means we have to add it to our kind of restrictions on our domains, right? We said, okay, I can't divide by 0. I can't take the square root of a negative number. And now the third one is I can't take the log of anything less than 0, right? In fact, not including 0. Or x has to be greater than 0 in a log. And so we have this new restriction on the domain of the logs. But let's take it back a little bit. What is the log? So a logarithm, we're going to call it base b, is going to look something like this. A log base b of x is the inverse of the exponential function base b, which is b to the power of x. We're going to talk about it. It's just it's the relationship between the two. It's just a fact. I mean, not just a fact, but yeah, but it stems from the definition of the logs. And so here, to answer your question, the inverse properties of logs says that log base b of b to the power of x makes x. Okay. Or I like to read it as if I have, let me just copy this here, copy, make myself some room. Maybe I can do it underneath this instead. Sorry. I'll just read ahead, I guess. What we're going to have is, how I'm going to read it is b to the power of x equals whatever's inside the log. Okay. But notice this relationship here is that log base b of something to base b to the power of x just drops out the x. Now this I would call the moneymaker, right? If you're trying to solve for something in the exponent and you need to drop it down, the way to drop it down is to wrap it up with log base b, right? Log of the same base, then you're left with just the x. Okay. Same thing, if you want to extract an x from inside a log, then you can take b to the power of the log base b, and it drops out the x. Okay. And so here, this is going to take some practice, of course, but this is how we will extract x from either the exponent or inside the log. Otherwise, you can't get at them, right? There's no way to get at the exponent without this law. And so, and you can't get inside the log without this law. And so here, this one, this is kind of, I call it the moneymaker. And we're going to work with it a lot. So b to the power of a is equal to c is equivalent to saying log base b of c is equal to a. Okay. And so I want to highlight this relationship because this is, I think, difficult. But if I have log base b of c is equal to a, and maybe I'll kind of just scooch this down here.
Is C still representing like the C in the other equation?
No, it's a new c. B to the power of a is equal to c. And so here, the steps are like this. So step number 1, b to the power of a, and then is equal to c. B to the power of a is equal to c. So if you wanted to rewrite this log as an exponential function, you're going to go kind of this loop, a loop-de-loop. And so log base b becomes b to the power of a is equal to c. So log base b of c is equal to a. Yeah, I know. I always have to take it nice and slow with this stuff. This doesn't stick with me naturally, but the only way I can get it to stick for myself is if I just kind of remember that, okay, if I have this sort of setup, then I can rewrite it as b to the power of a is equal to c. And I can just kind of go around in the loop. And so here, versus b to the power of a is equal to c, I think that's harder. But then I just kind of map it backwards to a log. And so what do I do here? Okay, I usually just write out this way and then I go in reverse, right? C is inside, A is the power, and B is the base. And so is equivalent to log base B of C is equal to A. For example, if we have to rewrite exponential functions in logarithmic form, okay. Two to the power of 3 is equal to 8 is the same as saying, okay, I know the base because the base is the same, right? The base of the exponent is b and the base of the log is b. So let's start there. B, oops, I wrote A. B is equal to 2. And I know that, okay, if I've got this written down, then I know, okay, then from log base B, so 2 to the power of A, which means that A must be 3, must be equal to, and let me use green, it must be equal to C is equal to 8. So what I get then must be a log base 2 of 8 is equal to 3. And you can always confirm, right? 2 to the power of 3 is equal to 8. That is what we had here. So even though moving from this direction to this, to the log, I find it difficult, right? But I can always check my work and say, okay, 2 to the power of 3 is equal to 8. And that has to be true, right? 2 to the power of 3 is 8. 2 times 2 times 2. So then I can do the same thing with the next one. And we can say, okay, well, I know B must be 5. A must be P, and C must be Q. So I'm going to get log base 5 of Q is equal to P. And I'm going to confirm 5 to the power of P is equal to Q. Take some practice. On your fancy calculators, you do have a log empty base button. So you are able to calculate the log of any base. So on your calculator, look for, it's going to look like this, log of kind of an empty base, empty entry button. We can confirm the first one, not the second one, because we've got variables in there, but log base 2 of 8 should be 3. So if I do log base 2 of 8, I get 3. Phew. So you can also confirm it that way. And this, or at least it's filled in for me. Something like that. A lot of calculators have just a log base 10 and a log base E button. For now, we're working with different bases, but those are kind of our go-to bases. We'll have to ask Allison what your go-to base is, but I feel like it's log base E. In a lot of sciences, it's log base E. But for now, we're working with any base. So now, this one's the easier one. If we have to rewrite like a logarithmic function as an exponential function, then we know that, okay, 3 to the power of 3 must be equal to 27. And you can check to make sure that's true. 3 to the power of 3 is 27. Phew. So just kind of getting used to that movement of 3 to the power of 3 equals 27 is going to be useful. How about the next one? 4 to the power of k is equal to n. Four to the power of k is equal to n. When would that be useful? That's going to be useful if you need to solve for n, right? Maybe you have a k and you need to grab the n, then you can rewrite it as 4 to the power of k is equal to n, and now all of a sudden you've got n is accessible. Okay. But if we have to solve log base 2 of x is equal to 4, right? So now we use that same move, right? Where I want to get at something inside the log. So I can rewrite this and I can say, okay, 2 to the power of 4 is equal to x. So then all of a sudden I just did it. I'm going to move this up because I think I'm going to need more room later. So here, step 1 and step 2. 2 to the power of 4 is equal to x, and 2 to the power of 4 is 16. So we did it. But notice, to extract the x from inside the log, we need exponents. I should say, sorry, not exponents necessary. Well, yeah, they are necessary, but we need the exponential function. Similar argument if you have to solve for x in the exponent. The way we do that is we rewrite it in log form, And so here we know, okay, 2 to the power of x is equal to 12. If I kind of unravel that into a log, I know it's log base 2. And then if I kind of follow the method, 2 equals x, and then 12 is on the inside of the log. Right, and you can confirm 2 to the power of x is equal to 12. So I'm saying the same thing because they're equivalent statements. Log base 2 of 12, from our calculator, we can do it. Log base 2 of 12. So x is roughly 3.58496250 and this is from the calculator, of course. The exact answer, this is the exact answer. This is just a number, right? Log base 2 of 12 is just a number. And so just like we leave fractions alone if we want to have exact answers, you leave logs alone if you want to have exact answers. But this is just to show you that it is just a number. It's kind of it's not an obvious number to me, at least. I don't see it, but. Okay, and so here, notice again, to extract the x from inside the exponent, or I'll just say from the exponent, we need the logarithmic function. Logarithmic function. Do I have, I'll scoot this down just a smidge. Maybe I'll zip that up just a little bit. Now here, note, many calculators only have 2 log buttons. Yours has the kind of open space log, and so that's because it's an engineering one, an engineering calculator, but many calculators only have 2 log buttons. Specifically, just a log. Whenever you just see log, this is the same as log base 10. It's called the common log. Log base 10 is for things like, so base 10, things like in physics, so sound, I'm pretty sure is in base 10. I'm not too familiar with log base 10 applications, but I'm pretty sure physics kind of has a hold on log base 10. For the rest of the sciences, we tend to use ln, and I write it cursive because it highlights to me that it's not a 1 or anything like that. And so that's going to be log base e. We've seen e before, Euler's number, right? 2.71828, blah, 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 right? Just like pi, it's just an irrational number. And so log base e is called the natural log. And so most calculators only have these two buttons, but we can get away with just these two buttons. Well, I'll show you the change of base formula. So you could do calculations of other bases. Log base 2, for example, in computer science, they use a lot of base 2 stuff. And so that doesn't really apply to you. So we're going to use log base E most of the time. In fact, just as a heads up, the natural log or ln, some people call it ln. I have a hard time doing that. I try to, but for me, this is the only log. And so sometimes I just call it the log, or usually I just end up calling it the log. I'm going to try not to, try to rein it in a little bit, but often if I say log, I mean the natural log. Okay.
We can just use the log, the first log form instead.
It depends on.
Sorry, the log with ranks.
Yeah, you can. Yeah. Here, so in writing though, if it says log like this, it's implied that it's base 10. Yeah. And so here, this is base 10. And I think you have an LN button and then just the empty base button, or at least I do. I have an older version of the calculator though, so does it look like the new freshie? Probably the same. They change anything. Yeah. Nice. Okay. Cool. So we could use our calculator. How about we start to think about rewriting these in terms of exponents instead, right? And then we'll check with our calculator, of course. But let's say A is the log of 1,000. That has to be equivalent to, this is implied base 10, so 10 to the power of something equals 1,000. So this has to be 10 to the power of x is equal to 1,000. 10 to the power, let's try it. 10 to the power of 2 is 100. 10 to the power of 3 is 1,000. Therefore, x is 3. So when you do the log base 10 of 1,000, you should get 3. All right, so let's try it. Log base 10 of 1,000, score. What if we have the log of 1 over 100? We rewrite this as an exponential function. I have this implied base 10. So 10 to the power of something equals 1 over 100. 10 to the power of x is 1 over 100. When we were playing around with 10 to the power of 2, I know it's 100, but now I have 1 over 100, which means that that's going to be the same as 10 to the negative 2, right? So x is negative 2, which you can play around with. 10 to the negative 2 is the same as 1 over 10 to the 2 by those exponent laws. And so that's why we need to be really flexy on the exponent laws. 10 to the negative 2 is the same as 1 over 100. Let's try it. So if I take the log of 1 over 100, log base 10 of 1 divided by 100, I do in fact get x equals negative 2, or just negative 2. Nice. How about C? And I'm gonna just change this color to be blue to match. The ln or the natural log is log base E. So I have the natural log of the root of E, which I can rewrite as E to the power of something is the root of E. Okay. But the root of E is E to the 1/2. Again, by those exponent laws. So X must be 1/2.
Just type the letter E. It's like, here's 1/2. So, yeah, I found the lowercase e and I just put it in there and it said it was 1/2.
Yeah, your calculator knows E. Yeah, just like it knows pi, or it knows an approximation. That's good enough. So you can try it on your calculator, right? If you have the natural log of the square root of E, and the E button is worth finding. Mine, it's in the red alpha menu down at the bottom. And so if I take the natural log of the root of E, I get 1/2. Let's see here. Maybe I'll do this. Okay. Wait. Magnetic. All right. Buckle up. I want the natural log of the root of, and then to get to E for me, at least, it's down here. So I need to hit the alpha menu to get to E. And then I can step it out. You don't have to close the brackets, but equals 1/2. Nice. Wait, okay. Make sure. There's a camera. Okay. Nice. So a lot of these you'll be able to confirm with your calculator. But it is nice to know those relationships between the exponents and logs, especially for later. What if you have to approximate log base 10 of 700 using your calculator? So you could just do it, right? But what are you saying? You're saying that the log base 10 of 700 is equal to X. Rewrite this as 10 to the power of X is equal to 700. Couple of ways that you could do it, right? You could try, okay, I know if X is 2, then I get 100, so that's too low. I could try X equals 3, and so, but then I know I get 1,000, and so that's too high. And so we already know X must be between 2 and 3. So what if we tried 2.5? 10 to the power 2.5. I get 316. So you can just try values. I didn't give myself very much room. Probably because I just used the calculator. But what we could do is we could let X be 2.5. I get 10 to the x is roughly 316.22. Bump it up. What about 2.8? 10 to the power of 2.8. Close. 10 to the x is 630.96. What if I do 2.9? 10, oops, to the power of 2.9. Uh-oh. Oh, 794. Too high. So then I go back to maybe x equals 2.85. 10 to the 2.85. 707, close enough. Therefore, x is roughly 2.85. Or on your calculator, log base 10 of 700, 2.84509.804. Let's see here. Or using the calculator, x is roughly still 2.84509.804. But before we had calculators, right? This is the procedure that they had to run through, right? To try to approximate these things. You would probably try to keep going. Once you hit 2.85, you're close, and then you kind of dig closer. Yeah.
My mom showed me some of her work from when she went to school, and her one question took up 3 pages.
Yeah. Yeah, logs can be, and we're gonna have some of those questions as well. Don't you worry.
It's about 3 pages of calculations.
Nice. That's great.
So don't worry, we're gonna get there too.
Why are you complaining? This is exciting.
Oh yeah,
No, we already know
it feels good.
We already know X, and then what's right after that, sorry.
We already know x must be between 2 and 3 because 10 to the power of 2 was 100 and 10 to the power of 3 from earlier was 1,000. So I already have an idea of the range, and so that's how I started. And then usually I kind of apply some computer science here. You go into the middle, and then you figure out where you need to go from the middle, and then you go in the middle-ish. Kind of use your judgment. But okay. So, oh, I can't rely on that clock. What time is it? Wow, acres of time. Nice. Yeah, I feel like my internal clock is all thrown off. I have no idea. Okay, so the exponent property says that, okay, log base b of a to the power of r, I'm allowed to rewrite that as r times log base b of a. Now, why is that important? Because notice that this guy, that r, that power, went down in front. So all of a sudden it's accessible. And so that's pretty cool, which means you can wrap up anything, any exponential function with a log, and the exponential or the exponent property tells you that then you're allowed to rewrite it as r times the log base b of a. Right? Of course, you're allowed to move in the other direction as well, right? And sometimes we do to simplify things, but usually I use it in this direction where I use a log to try to move that exponent down in front. And so here, let's try something like this. So if you want to try to solve 5 times 1.3 to the x is equal to 10, you want to try to figure out what x is. That's not the easiest thing, but the first thing you want to do is you want to isolate the exponential function. Okay, you don't want to have 5 here because 5 isn't to the power of x. And so the first move is going to be to move this 5 over to the right-hand side so that you're just left with the exponential function. So step 1 is isolate the exponential function. In this case, 1.3 to the power of x. So what we'll do here is we'll have 5 times 1.3 to the power of x is equal to 10. So 1.3 to the power of x is 10 divided by 5. Bless you. I'm going to go for 2. Then the next step is to apply the exponent property. Apply the exponent property by taking the log of both sides. As long as you're doing it to both sides, then you're safe. You're allowed to do that. By taking the log of both sides. Kind of a fun fact, you can take the log of any base. Sometimes we use a convenient base, but for me, as my go-to, I'm going to use the natural log. Yeah. So how about this? An LFF, a little fun fact. We can use the log of any base. The log of any base. And my default is the natural log. Let me bump this down here. So coming back here, if I take the natural log of both sides, then I get the natural log of 1.3 to the power of x is the natural log of 2. The natural log of 2 is just a number, right? So, okay, that's kind of, you can just leave it as is. But the reason we took this log is that now I can rewrite this as x times the natural log of 1.3, which again is just a number. So now I have x times the natural log of 1.3 is the natural log of 2. X is just multiplying the natural log of 1.3, and so I can solve this. Uh-oh. I need this to be just a little bit smaller for now. So then x is going to be the log of 2 over the log of 1.3. Which are just numbers. but I'm gonna leave it in exact form. Okay. So here, this is the answer in exact form. Whee! We did it. Let me add a page here. I have too much to say. Okay. Well, I'll rewrite that. Let me bring this down here. If we go back here, so either way, we still have to isolate the exponential function, but here I just said, oh, let's just use the natural log. I don't care which log, but a more convenient base might have been log base 1.3, which we can do, but it's kind of weird. So from here, we used the natural log to solve 1.3 to the power of x is equal to 2. But this is a base of 1.3. So we could have used log base 1.3. A more, I'm going to say convenient in quotes, because I don't think it's actually that much more convenient, but it is a little bit cleaner. A more convenient base would be b equal to 1.3, which would look like this. The log base 1.3 of 1.3 to the x is log base 1.3 of 2. Same thing applies, right? I'm allowed to bring this x down front. That's why I'm using the logs. So I get x times the log base 1.3 of 1.3 is the log base 1.3 of 2. I chuckle every time. It's so funny to me. Log base 1.3. But why is this a more convenient base? Because log base 1.3 of 1.3 tells me that 1.3 to the power of something has to equal 1.3. Well, that's just 1, right? And so here, 1.3 to the power of x equals 1.3. So x is equal to 1, which means that that whole thing is equal to 1. So I get x times 1 is equal to log base 1.3 of 2. X times 1 makes x, so x is log base 1.3 of 2. Huh. So marginally more convenient. I don't think it's that much more convenient, but we do have a simpler log on this side, right? We have log base 1.3 of 2. In comes the change of base formula. So here, the change of base formula says that, okay, if I have log base b of a, that's the same. I can rewrite it as log base c of a over log base c of b. So here, if we consider log base 1.3 of 2, I'll use a different color. consider log base 1.3 of 2, then b is 1.3 and a is 2. If I want to convert it to log base e, which is what I used, right? Instead of log base 1.3, I used log base e. And so now convert to log base e, which is the natural log. Okay. Then I can follow this, right? Log base 1.3 of 2 is the same as log base e of 2 over log base e of 1.3. Neat. So log base 1.3 of 2 is log base e of 2 over log base e of 1.3, which is the same as the natural log of 2 over the natural log of 1.3. Which is what we found earlier. This is the answer we found earlier. Maybe I'll say initially. Of course, you can, as long as you have the same log base here, you can zip it up into one tidy log if you wanted to. It would be log base 1.3 of 2. Right? And so we can work the change of base formula in either direction. And so sometimes you might find an answer that looks different from a friend's answer, but then once you apply the change of base formula, they're actually the same. Nice. And so by that logic, right, this is why we can use the log of any base, because then as long as I'm dividing the same base, the log base, right, I can zip it up into one nice log later if I wanted to. Nice. So kind of sneaky. So we have the fancy log base, the empty base button. Okay. But like I said, a lot of calculators don't have that button. They only have log base 10 and log base e. So then if you want to find the log of any base b, you would use either log base 10 or log base e here, as long as you're consistent. And you can calculate log base 10 or log base e of a over b. So find log base 14 of 3. I guess this should say using only the log base 10 or log base e buttons. So we have log base 14 of 3. You could rewrite this as 14 to the power of something equals 3. That's going to be relatively difficult, right? And so we'll use the change of base formula. So here in the change of base formula, b is 14 and a is 3. And the change of base formula, bump this down here, says that the log base b of a is the same as log base c of a over the log base c of b. Let's use, should we spice things up and use log base 10? Why not? Let c be 10. Because you have an ln button, that might be the easier choice, but it doesn't matter. We'll find the same answer. And so if I rewrite log base 14 of 3 is the same as log base 10 of 3 divided by the log base 10 of 14, which if I use my calculator, log base 10 of 3 divided by the log base 10 of 14, I get roughly 0.416289669. You can check on your calculator. Okay. Check on your calculator. Since you have the fancy button. Log base 14 of 3, phew, 0.416289669. You can try it with log base e. Log base e of 3 divided by the log base e of 14, we still get the same answer. So it doesn't matter as long as you use the same log base over here. Okay. Any questions about those log laws? What is it? Bob Loblaw's law blog?
Yeah.
Always- Yeah,
Yeah.
I know. That's what I always feel like when I say log laws. It's from Arrested Development, which I guess is kind of old now. It is weird. There's quite a bit of pages that I have to add for work here, but let me see. I'll bump these down. But since I know people are are printing these out, I didn't want to use a ton of empty pages. Really stepping up our game here. If we have to solve this thing, this monster, first thing we're gonna do is, okay, I have an x in the exponent, which means I have to isolate the exponential function still. So let's start there. Step 1. Isolate the exponential function. Move everything that's not the exponential function over to the other side. So I get 6 times e to the 3x plus 1 is equal to 9. So e to the 3x plus 1 is 9 divided by 6. 3, do you want to use the fraction or the 1.5?
1.5.
1.5 it is. Okay. You can use the fraction if you want to, but because it's nice and clean, we can use the 1.5, that's fine. Okay. Now, we can consider the base here. Luckily, it's my go-to base anyways, and so I'm going to use the natural log, 1, because it's my favorite, but 2, it is base e, and so it's going to have that kind of magical turn it into 1 property, right? And so step 2, take the log, can be any base, but I will use base e, but I will use the natural log of both sides. That's so important, and it's the step that people love to forget, is that you have to also take the natural log of 1.5 of both sides. And I shouldn't just say people, I love to forget it as well. So I take the natural log of e to the 3x plus 1 is the natural log of 1.5. Doesn't matter how complicated the exponent is, this whole kit and caboodle, we can move it down front. As long as you remember to keep brackets around it, because it's now one thing, multiplying the natural log of e. So we get 3x plus 1 times, are we ready to just go to 1?
Yes.
Nice. Is the natural log of 1.5. And this is 1, since the natural log of e is equal to 1. E to the power of 1 is e, and so this, the log of, or the natural log of e is just 1. That's worth kind of committing to memory as well. You can talk yourself into it every time, but eventually you're just gonna write 1, and that's fine. So now all of a sudden I have a relatively simple left-hand side is equal to the natural log of 1.5. And so I have 3x plus 1 is the natural log of 1.5. And so now I can solve 3x plus 1 is the natural log of 1.5. Treating this as just a number. The log of 1.5 is just a number. I don't care really what it is, but solving for x, I subtract 1 from both sides, and then finally I divide by 3 on both sides. And so I get 3x is the natural log of 1.5 minus 1. So x must be the natural log of 1.5 minus 1 divided by 3. We did it. You can plug this in. The natural log of 1.5 minus 1 to the power of 3, as long as you're not rounding, you can multiply it by 3 and then add 1, right? And then take e to that, and then take the log of it and find that it's the log of 1.5. Kind of, you could check your work. I never do, because it's a lot of kind of reverse engineering. But you could, in theory. Pretty fun, right? Any questions about that one before we do the next one? Okay. Don't worry, we've got word problems too. If we have to solve 2 times 1/2 to the t plus 6 is equal to 10, right? We follow those same steps. And what I'm going to do is I'm going to give you a moment to isolate the exponential function and then take a log, any log, and try to solve for t. I'll even pause the recording so it's not a ton of dead air here. Pick this up again. All right. To my pen. I'm not going to write out the steps this time, but I do follow the same steps, right? And so let's start with 2 times 1/2 to the t plus 6 is equal to 10. Chipping away, isolating the exponential function, which is this little guy, right? 1/2 to the t. So everything else has to be moved over to the right-hand side. And so I'm going to have 2 times 1/2 to the t is 10 minus 6, which puts me at 4. So 1/2 to the t is 4 divided by 2, which I'm going to say is 2. You could look at this exponential function and rewrite it as a log, right? Log base 1/2 of 2 is equal to t, kind of reverse engineering it. But let's not do that. Let's do it the easier way and take the log of both sides. I'm going to use the natural log. So if I take the log of 1/2 to the t is the log of 2. Let me bump this down. Now I use the log property that I can rewrite this as t times the natural log of 1/2 is the natural log of 2, which means that t must be the natural log of 2 over the natural log of 1/2. By the change of base formula, right? Using the change of base formula, t is log base 1/2 of 2. Let me clean this up. Which we could have seen here, right? But it's not obvious to me, so I always just apply the logs. But if you get kind of nimble enough with looking at these exponential functions, then you could jump in here and say, okay, well, that's the same thing as log base 1/2 is equal to t of, and then of 2. And so from here, we could say that this is the same thing as log of 1/2 of 2 is equal to t. With practice, or not, can be like me and just always take the log and not worry about this. Right? But that is the same. Log base 1/2 of 2 is t. T is the log base 1/2 of 2, or using the change of base, the natural log of 2 over the natural log of 1/2. Let's see if I can. Okay. Tuition is currently $1,050. Wow. And is growing 7% each year. And we want to know, when will tuition exceed $2,000? And so just in general, we can sketch out, I've got probably something like this. We know the general, it's growing, right? And so I know I have exponential growth. And I know the general formula for this is a times b to the power of x. But b could be rewritten as 1 plus r. or f of x is a times 1 plus r to the power of x. And that's all from last day, which I guess was last week, so rude of me. But we did talk about those functions, and you'll have them on your formula sheet, and so, which I should put together for you, so you can have it. Right, and so here, R is, let's see here, R is 0.07. So we know that f of x is a times 1.07 to the power of x. We have, we know that if x is 0, then f of x must be a, right? And so regardless of which one of these we use, f of 0 equals a. And so what would be nice is if I let, use this, let x be 0. We could have used t as well, but then the tuition, f of 0 is 1050. That's where we're starting. So that's here. 0 at, so currently 1050. And we want to know at what point is it going to exceed 2000. So at some point, this thing is going to be 2000. And then after that point of x, it's going to be more than 2000. And so what we need to do is we need to find a, and then we have a perfectly reasonable exponential function. And so here we have f of x, or f of, let's use the pink again. F of 0 is a times 1.07 to the power of 0, which is equal to, we were told, 1050. So a must be 1050. Therefore, f of x is 1050 times 1.07 to the power of x. What color haven't I used? Light blue. We want to find x when f of x is 2000. We can do that. If I force this to be 2000, is 1050 times 1.07 to the power of x. All of a sudden, I know how to solve this, right? Because this looks exactly like all the other ones that we were just solving. I have to isolate the exponential function, which in this case is 1.07 to the power of x. So I need to divide both sides by 1050. So I get 2000 divided by 1050 is 1.07 to the power of x. 2000 divided by 1050. Let's see if I get something nice. I do not. I'm just going to keep it as is. Be kind of lazy. Guess I should make it look like 50. I get kind of a nasty number, but I can take the log of both sides. Any log. You could, in theory, you could use log base 1.07. I think that's kind of extreme, but it'll work, right? And then you'll just be left with the log that you want, because log of log base 1.07 of 1.07 is just 1. And then so you'll have the log base 1.07 of 2000 over 1050. But let's take the longer way. Take the natural log of 2000 over 1050 is how about I do the maneuver right away, because it's the reason I'm taking the log is to bring that x downstairs. And so I have x times the natural log of 1.07. Already moved. Because that was the goal of taking the logs anyways, so you are allowed to make that leap of, okay, once I've taken the logs, I can bring that exponent downstairs. So then x, doing a little mind stretch here. I am using my revolving door and I'm writing x on the left-hand side because I can't handle it. But then x is the log of 2000 over 1050 divided by the log of 1.07. Or by the change of base formula, because, boy, I wanted the pointer. Because I have the same log base here, this is the same as log base 1.07 of 2000 over 1050. But either way is right. Right, I would probably stop here. I don't need you to zip it up. But if you use log base 1.07, it would look like this. Nice. As a summary, we've already done this a lot already, but solving exponential equations, you have to isolate the exponential expression if you can, then take the log of both sides, log of any base, and then use the exponent property to bring that exponent downstairs, and then use algebra to solve for the variable. This is just a summary of those steps that we were following. I guess I kind of stopped after step 2, or stopped calling them steps. Then you just solve. Okay, I'm gonna leave this as review for next day, but I encourage you to try the remaining 2 examples on your own, and then we'll use those for review next day. If you have any questions, let me know. Otherwise, I'll see you on Thursday.